It's just a little bonus, a little bit extra on attribute information. We talked a little bit about, different kinds of numbers, text, and so on. And so I wanted to just add a bit about attributes. They are stored in a database. This is a collection of data stored in some kind of a structured format. Mostly we see this represented as a table like this here, something that looks very spreadsheet-like. And a table is something that has rows. So rows go across, and columns, which go up and down. An attribute field would be in the columns. So here, this is the feature ID, the shape, and this is kind of an internal that links to the actual polygon or whatever, point or line or whatever. Then, here, and these are custom attributes: the name of the feature, the state name, some type of code that represents it for what state it's in, code that represents the country, and some other combination of those, or actually county that must be. And this would be a combination, what's called a Federal Information Processing System code, something that is like a identifier for the state or the county. And this is just an example of, so you would have for each polygon in the GIS, and this apparently would be, I guess, lakes. This one would be Lake of the Woods is the name of it. It's in Minnesota. The FIPS code for Minnesota is 27, and whatever county that is, the code would be 077. And then oftentimes you'd have codes like this so you can kind of link together other information maybe. So an individual record, right? This is a individual record, and this is a attribute field, right? So the FIPS code for this record, it would be the thing that's under FIPS, and then in this row. So here you have individual counties. You have the name, so you have the GIS features, and then the attributes, you have the name, the FIPS code, population area, population density, and these are attribute information that go along each one. So one row goes along with one feature. Now, one thing I mentioned in class about the difference, this is with vector data. So for each polygon or each line or each polyline, right, polygon, polyline, or point, sorry, you would have a single record. And you can have as much attribute information tied to that feature as you want. Now with raster data, the raster has to be, you can't have different information for every pixel. What you would just have is every pixel is assigned a number. And then you can have a lookup table where that number means something, like in a lookup table. But it's really impossible to store. It's just not practical anyway, to store attribute information for every single pixel. So each pixel just has a number because it's like a big grid of numbers, but you can have an external lookup table that references those numbers and has information that goes along with it. So for example, you could have a raster with FIPS codes, those are numbers, and then a lookup table where this FIPS code goes along with this name. But every pixel within Watcom would have the same number for this, and then it would look up to the name and so on. So rather than one record for the whole polygon, you would have just numbers for for all of the pixels, and then they would have a lookup table. Here's another one with more information: name, surname, address, phone number, and so on. And these fields or columns, they consist of different types of data. as we mentioned. So generally numbers, text, sometimes they're called string, text information, alphanumeric characters, or dates. And those are the basic types. There's a few kind of fancier ones for the that many of the newer GIS data structures can hold, such as maybe pictures or other types of digital information. But really the basic types are numbers, text, and dates. But when it comes to numbers, there's different ways to represent numbers, and each different way has different storage requirements. So, for example, if you're, there's maybe what's called a short integer. And a short integer can't store a big range of values, but if you only need like the numbers 1 through 100, it works just fine. But if you need to store values that go into the millions and billions, you need to have a different type of numeric value to be able to contain all of the different variations. And so I'm going to go on a little bit of a sidetrack and talk about like numbers and computers. So for your attribute or your other data, computers use something called binary, and binary is like a switch that's on or off. So it's represented by a 0 or a 1. That is that's like 1 bit of information. 1 bit is a computer being able to say it's 1 or is it 0. And what happens is that you take multiples of those bits and you can use those to get more detailed information, but under the hood, it's just a series of zeros and ones that are happening. So that's the smallest kind of sort of molecule of data in a computer is a bit, 0, 1. So let's say if you have a raster of 1-bit numbers, they can have 2 values. They're either going to have zeros or they're going to have ones, because that's 0 or 1. So you have a 0 or you can have a 1, and and the way it kind of, you'll see as we go, it's like this is 2 to the power of 1, because it's like 2 to the power of how many bits. That's how many values you have. 2 to the power of 1 has 2 values, 0, 1. But if you add more bits, in other words, if you have 2 different bits, you can kind of get more range of values as you go up there. So if you have 2-bit numbers, how many different values can you have? So if you have, instead of 1 number, which is 0 or 1, you have 2. Better, let me just show that. You can have like this. So instead of 1 or 0, if you have 2 different bits, you can have 4 combinations, or 2 to the power 2. 0, 0, 0, 1, 1, 0, 1, 1, 4 different combinations. If you have 3 bits, it's 2 to the power 3, 0, 0, 0, 0, 1, so on and so on and so on. And so you have 8 values. And so every time you add a bit, you're increasing the power by, you're doubling the power. So for example, there's something called ASCII text, where each letter or number or space or punctuation is represented by a 7-bit value. It's a kind of an older way of representing printable English and control characters. Nowadays, computers use something called Unicode, which is has more bits than that, so that we can include international characters as well. And oftentimes, what's very common to use in computer applications is 8 bits. Which represents 1 byte. A byte is, so you know how your hard drives have megabytes and gigabytes? That means like 1,000 or a million or a billion bytes, and every byte is 8 bits. So times 8, whatever that is, times 8 is how many bits you have. So 8-bit would be 256 values. So if you look at a color picker, for example, in computer applications, oftentimes you have values from like 0 to 255, because it's an 8-bit color, and that's very common. Here's an ASCII code chart. You have, and I think I'll just jump past that and to not get distracted. So here's how many values. So if you have no bits, no values, 1-bit number can represent 2 values, 2-bit can represent 4. And as you go up in bits, it doubles and doubles each time. 8-bit is a common for computer applications. You can have 256 values. 16-bit would be, you can have up to like around 65,000. If you go up to 24-bit, like 24-bit color, you might hear in computer applications, that'd be like 16 million. 32-bit, you can have, 4 billion here, and so on. So sometimes you might hear of computers being, software being 32-bit or 64-bit, and this is kind of what they're talking about. How many values can be represented by, at an individual level. So a long way to say that there are different types of numbers you can store in a database. You can have what's called the smallest one is 2 bits or 16. I'm sorry, 16-bit or 2 bytes, and that can hold numbers from negative 32,000 to about 32,000. So it can easily hold numbers that are in the range of like a few thousand or so. If you have more than that, if you're getting up to the millions or even into a little bit into the billions, you can have one that it stores twice as much space, but it can have a bigger range of numbers it can store, called a long integer. These are integers, so it means they don't have fractions, like they're just whole numbers. If you do get into decimal numbers, like with fractions, you get into what are called smaller ones are called floating point. Those are 32-bit. Those are numeric, and those go from this is a little easier on our chart here. You can go from like negative 2 billion to positive 2 billion. Or you can, if you need more than that, you can have a double, which it goes to 64 bits, and it's just like way more information that you can need. Because you also have to remember, one reason these take up more space is because of the decimal place as well. That these have the double, particularly, can have very, very precise decimal. So if you're just going, like, if you just need ranges of 1 to 99, short integer. Now the temptation is to say, well, why mess around? Why don't I just make everything a big, as big as possible? Well, it's just to save space in the long run. Your data, if you have a huge data set, using the smallest type that you can get away with will save you space. But as these days, you're often, especially with a small application, you're often safe enough just using a big number type. But let me show you where you would find where this would come into practice. If you're working with attribute tables, like in ArcGIS Pro, for example, you can add a new attribute, and you have choices here. And that's the reason I'm going through this, is to explain, like, why is it asking me if I want what's a long, what's a short, what's a float? What are these things? These are just different ways of storing numbers. Short integer, this is good for numeric values that you're not going to be ridiculously large. If they are going to be ridiculously not large, but they're whole numbers, you can store them as a long integer. If you need a decimal place, but not a big range of decimal place, accuracy, you don't need a whole ridiculously large range of numbers or accuracies. You can have a floating point number. And if you do need ridiculously accurate, go big, go double. So double is even, more detailed as far as the decimal places go, the range of numbers. And so that's the difference here. And there's other field types as well. Text and date are kind of common and translate well between different platforms. However, there's some ones that are kind of unique to the new GIS databases in products like ArcGIS Pro, what they call a geo database that they use. They can have what are called blobs, which blobs mean binary large object. It means like you can actually store like a digital photo in an attribute table, which is kind of crazy, but I guess you can do that these days. Something called global identifiers, which I'm not that familiar with, but essentially it's some type of way it's something that allows you to interact with like an enterprise level database. I don't know enough to help you on that one, tell you the truth. And then apparently you can even store raster data in a database, which is kind of cool. All right, so this is just a really long way to kind of explain a little bit about, how computers store numbers, so that just to help you understand what are these different options for different kinds of data, particularly number data, and what's that about. All right, thank you.